everyone else has said what you're going to say. So apologies for any duplication here. Okay, so when people come to us, they come with certain preconceptions, misconceptions about natural fibre insulation, and that influences their opinion of the material, where they might want to use it and where they might not want to use it. And most of the time, well, some of the time certainly, it can be a hindrance. So hopefully in this talk, I'm just going to go through a few sort of common points that we come across. The main areas we're going to talk about: carbon savings, fire, getting insulation wet is a frustratingly common one, summer overheating, and also cost. So not in any particular order. Okay, so aren't all the carbon savings the same for all insulation? You know, if you use wood fibre, if you use PIR, if you use fiberglass, you know, what really is the difference? It's a fairly common viewpoint and understandable, but that does only look at the energy savings that are provided by the insulation itself, and completely ignores the embodied energy of the material and the associated CO2 emissions from from producing that material. Wood and all natural fibres absorb CO2 to grow, and that gets incorporated into the product when it's produced. And in the case of wood fibre particularly, you end up with something that's carbon negative, so it's actually removed CO2 from the atmosphere. Mineral-based insulations tend to produce CO2, and they're net CO2 producers when they're manufactured. So if we look at a retrofit scenario, we're going to look at, say, external wall insulation, and we're just going to look at the heat loss through the walls as well, not the roof and the walls, and not the roof and the windows and the floors and ventilation losses, etc. We just look at the walls, and if we were to use 120 mil of EWI insulation, which is pretty common, if you looked at the CO2 emissions just from the insulation, and again the render and the fixings and all the other components are probably pretty similar to the two systems, so we're just going to focus on the insulation. But if we look at the mineral wool bats, typical mineral bat will produce about 15.7 kilos of CO2 per square meter, whereas wood fibre boards are actually locking up, so they're removing 23 kilos of CO2 per square meter. So, that's nearly 40 kilos a square meter difference. So there's a massive difference in the carbon impact of those materials that you're using. Let me get my little pointer out. So in terms of what that looks like in some figures, here we have so basically this chart here is showing us the typical gas heating related carbon emissions for a solid brick walled house, starting U value of around about 2, finishing about 0.29, so 85% improvement. So you think really, really good. We are assuming internal temperatures of 18 degrees, and we're looking at an October to March average for the Midlands, which is about 5.3 degrees. So anyway, during that heating period, say between end of September, beginning of October, and up to the end of March, on average we're releasing 4.5 grams of CO2 per square meter per hour through the heating that we are using to maintain our 18 degrees inside. When we put our insulation on, that goes down to 0.66. So I think brilliant, we're making a massive difference, and yes, you are. But when does that actually have overall a net benefit to the environment? So when we start including the embodied energy, it's actually 167 days before that house that you've just retrofit actually is producing less carbon overall than it did before the insulation was installed, i.e. the reduction in carbon emissions it takes 167 days to offset the emissions produced by producing that mineral wool bat. Wood fibre is quite the opposite. So you actually go back in time with wood fibre. You've actually soaked up 246 days of running your house. So, there's 400 days between them. But if you assume that we're only heating a house for, 180, maybe 200 days a year, it's actually well over a year the difference between the two is well over a year. So really, it's absolutely vitally important that if we want to make a difference to our carbon emissions right now, and rather than at some point in the future, we really should be using a lot more plant-based materials. If you want to see a little bit more of a deep dive into that, there's an article on our website which you can see through that link. So the next one then, doesn't wood fiber just burn in a fire? You know, why would you use something that's going to burn in a fire? Wrong button. So natural fiber insulations do burn in a fire, and so you'd assume, I'm not going to use that. That's unsafe. But the density of materials has a big impact on how quickly they burn. So very dense materials burn very slowly, but they also, particularly in the case of wood fiber, burn very predictably, and it's that predictability that makes them actually quite safe in a fire. So should they catch fire, you know what's going to happen. The fire spread is very slow. Everyone knows, essentially what's going to happen. In very intense fires, they don't really release much smoke. And bearing in mind that the fire is inside a building, it's not within the wall of the building. So it's not, the first thing to catch fire will be all the stuff that's inside the house. So anyway, should you have a fire, the wood fiber, it doesn't produce much smoke. It doesn't drip burning droplets, which is another issue with certainly plastic-based insulations like polystyrene. And also, in the case of materials like PIR and mineral wool, although they're not combustible in some cases, when you heat them, you do get hydrogen cyanide and hydrogen chloride coming off of them. So the wood fiber doesn't release those kind of products. And if you do get even a lungful of either of those gases, you're in serious trouble. And assuming that you are still alive, then it really does hamper your escape from a fire. So the assumption that they're very dangerous to use in a fire, excuse me, in terms of the natural fibers, is really not correct. So Seb's obviously gone through this in rather more detail than I'm going to cover here, but just quickly looking at the building regs. Generally, Part B, when we're looking at external wall insulation, Part B requires a B-rated S3D0. Now, the just in case for anyone who doesn't know, the letter in the rating gives you a fire rating in terms of how much the material contributes to a fire. So you've got A, which doesn't contribute at all, B, which doesn't really contribute, and all the way down to F, which contributes a lot. The S figure gives you the amount of smoke that's produced, and the D figure gives you the amount of flaming droplets. So S1 means it produces very little smoke, and D0 is it doesn't produce any droplets. Anyway, having a fire rating for rendered wood fiber of B S1 D0 means that it passes building control requirements up to 11 meters. Unfortunately, last year the limiting height on any sort of combustible material or any material that isn't A2 or better fire rated was brought down to 11 meters. But we can do EWI up to 11 meters, which is probably going to cover most buildings in the UK, or certainly a very large proportion of them. We've also got specs for timber frame structural walls, and I know Seb said there were a lot of specificity to them, and yes, there is, but there's also organizations in Europe that create quite generic specs, and certainly multiples of specs that give you a good sort of range of specs to choose from. So we do have a range of REI 60 specifications, which means you've got 60 minutes fire protection from the inside, 60 minutes from the outside. So you can use these walls on boundaries or within a meter of a boundary. And you can have rendered or clad surfaces on the outside. Generally, for sort of domestic scale stuff, roofs tend to be rather simpler, especially because you can still use type 1F felt, which is quite incredibly flammable. Essentially, you just need to have a mineral surface, i.e. a tile or a slate. And then when you've got multiple housing, you need to have masonry fire separating walls. So roofs are relatively simple. Structural walls, a little bit more involved, but certainly all the information is available to actually get all of these materials through building control. A little sort of examination here of what one of these external walls looks like. So the important thing is that you've got a 60mm wide stud. It's not a normal 47 or 50mm stud. You've got 15mm OSB, you've got a vapor control layer, you've got an insulated service cavity on the inside, and then you've got basically a double layer of plasterboard. You've got a fire-rated plasterboard and then a fibrous gypsum board, i.e. Thermacell. Externally, you would use a much denser wood fiber board than normal, so it'd be 180 kilo cube board, which is not the normal sort of dry fiber that most people sell. And then that would be finished with a render. Steiker also have some specs with B2 rated finishes, such as treated timber, that kind of thing, so you can do clad finishes as well. Again, a bit more of a deep dive into that if you want to have a look on our website. Okay, the other one that we get a lot, doesn't wood fiber just fall apart when it gets wet? Doesn't it? I think people assume it's some sort of form of paper mache, and as soon as it gets wet, it just turns to mush, and that's it. To be fair, most of the time in the UK, you'll have, if you're building a timber frame, or even if you're just building a timber roof, you'll have all your nice dry components, you'll put it all together, and then the heavens will open and whatever you've built will be soaking wet. So when you're working with wood fiber, it can actually be left exposed for up to 3 months. It is really quite robust in rain, in water. After 3 months, there's nothing wrong with the product. You just get a bit of surface staining, which doesn't look great. So people tend to put that sort of limit on it. But actually, wood fiber transports moisture incredibly quickly. That's what it does in a plant. It transports it from the ground all the way to 10, 15 meters in the air. It does that really, really effectively. It's great at dispersing water very effectively as well. So if you've got timber structures, you've insulated them, they get absolutely soaking wet, the wood fiber will help them dry out faster than any other insulation material. So when you're designing timber structures, you really should be assuming that they're going to get wet, because 99% of the time they probably do. And so you need to consider how you are going to actually dry that structure out. And slow drying of structures really does cause problems in both structural timber, but also particularly in sheet materials like OSB or ply. When you use wood fiber within these kind of constructions, it really does change the risk factor that contractors on site are exposed to, in terms of what happens if it does get wet. For example, if you're using mineral wool or fiberglass, more often than not, you really should throw away the soaking wet insulation and put dry stuff back in. The other thing is that when timber gets wet, obviously it swells, and as it dries, it shrinks. If you're using PIR, rigid boards, that kind of thing, and you're insulating timber frames with that, not only does the PIR shrink, but the timber shrinks as well. So you end up opening up quite a few voids within the structure as it dries. Wood fiber tends to be quite a flexible material, and so as timber dries, it would expand and fill around those timbers and prevent any void formation. As I say, glass wool and mineral wool dry incredibly slowly, if at all. They are vapor permeable, so you might assume that because they're vapor permeable, they'll dry just as quickly as anything else. But their inability to transport moisture through capillary transport, which is by far the fastest method of transporting moisture around, and their lack of hygroscopicity does really make a difference to the speed at which it all dries out. And again, if you're using PIR in panels, that massively hinders. In terms of voids, then, if you open up voids within a timber structure, you've got a network of channels for air to move through, which means that as soon as there's a wind, you're losing more heat from that panel than you expect. So it's really important when you're designing timber structures to accommodate or to understand that you want to avoid any void formation and use insulation materials which are going to prevent that. In addition, wood fiber is really good at buffering humidity, particularly in historic timber. And so it's amazingly good at preventing accumulation of moisture in timber, particularly when it's used for internal wall insulation and preventing the associated decay. And so it's ideal for building renovation. So the assumption that wood fibre is just going to sort of turn to mush if it gets wet, is about as far wide of the mark as it could possibly be. So actually it works extremely well in damp conditions to help everything dry out. Okay, don't all insulations keep you cool in the summer? Bit of a rehash of something I've said before, but we still get this quite often. People assume that if you just stuff enough insulation into a structure, yes, it'll keep you warm in the winter, but it will also keep you cool in the summer. And again, it's sort of based on the assumption that the U value dictates how much heat is transferred through there. But U value is based on thermal conductivity, which is based on a steady state measurement of heat flow. So steady state means that when you start heating something up, at some point you will get a steady heat flow through that material. The thermal conductivity measurement is agnostic effectively about the time taken to reach that steady state. It just tells you ultimately, how much heat will flow through it. In our environment, the external temperature changes pretty much continuously between about February and, I don't know, October, November. There's wide fluctuations every day. And so knowing what the steady state performance of a material is not necessarily that useful, because it's most of the time we're not in a steady state. So if you use something called thermal diffusivity, or if you look at something called thermal diffusivity, it's the property of insulation that gives you an indication on how long it takes for heat to actually travel through that material. It tells us how quickly temperature changes propagate through it, which then in turn allows us to calculate something called decrement delay, which is the actual time it takes from heat to hit the outside of a building, work its way through and get to the inside. I'm talking about summer mainly because it's really easy to keep a building warm in the winter. In terms of a relatively new building, we pack so much insulation into them that keeping them warm in the winter is pretty easy. It's actually keeping them cool in the summer that is becoming much more of a challenge. So table of doom, which I have shown before, so apologies for this. This is the column that most people are going to be looking at. They're going to be looking for PIR 022, possibly down to 0.018. Brilliant, that's the one for me. It's going to make me really thin walls with good U values. Let's do it. You probably wouldn't, you might look at these and think, a bit high, but anyway. If you're interested in acoustics, you might look at more dense ones and think, okay, a bit more density there, that might be beneficial for acoustics. But probably most people don't look at the specific heat capacity in this column. You combine these three properties and you get this property, thermal diffusivity. And the higher the figure, the faster heat moves through it. So bearing in mind that we're cladding our buildings left, right, and centre with polystyrene, and polystyrene allows heat to move through it quicker than absolutely anything else on this list by quite some margin, is a shame. Anyway, so PIR might be the obvious other one. Actually, the diffusivity of PIR is relatively low, but still, even a quarter of that again is materials like wood fibre boards. Turning that into something that's hopefully a bit more understandable, if we calculate the decrement delay for a roof that has a U value of 0.13, we can see how long it takes for heat to hit the outside, work its way through and start coming inside. This is really, really relevant if you're working with mansard constructions, loft conversions, any sort of room in the roof type work. They tend to be the areas that have the biggest biggest temperature differentials in the summer. So you can quite easily have a surface temperature somewhere between 50 and 60 degrees. And obviously the inside of the building, you're trying to keep somewhere in the low 20s. So, just less than 3 hours with polystyrene, just over 3 hours with fiberglass, and fiberglass would be a common one to insulate your roof with. So if the sun comes up in the middle of summer, sort of 7, 8 o'clock, by maybe 10, 11 o'clock, you've got heat actually piling into that room. So, it's good by lunchtime, and by the peak, which is normally 3, 4 o'clock in the afternoon, it's going to be toast in there. Wood fibre, then you're looking at about 15 and a half, getting on towards 16-hour decrement delay. So it's 16 hours before any heat actually works its way through that structure. what tends to happen is the wood fiber boards on the outside soak up most of the heat. The sun goes down, the external temperature cools, and that heat then radiates back outwards again. So you get very little heat actually going through the fabric of the building. Obviously, we're not talking about solar gains through windows and other openings, but yeah, just through the fabric gains, and they tend to be some of the largest ones in mansard and loft situations.
Last minute, Chris. Thank you.
Oh, bugger, really? Oh, sorry, excuse me. Oh, I'll be quick. Right, very quickly, just to show you. Is it really? I'm like a time machine here. Just to show you something a bit more practical. So we took some boxes, wood fiber box and a polystyrene box, same U value, same thickness, same design, same design. We put them outside and brought them back into a room. We let them cool down. You can see the wood fiber box cooled down to 6.5 degrees. The polystyrene box was a little bit colder. Anyway, I'm going to have to rattle through this. Sorry. Anyway, after an hour, the wood fiber has gone up 2 degrees, polystyrene has gone up 11 degrees. And this graph really shows you inside those boxes, and bearing in mind that there's no jiggery-pokery, they are absolutely identical in the same place. The only difference is the material. The wood fiber goes up nice and slowly here. The polystyrene temperature inside that goes racing up. So that's a fairly clear example of what U value doesn't tell you about how quickly temperature moves through a structure. Actually, I might just be able to quickly whip through. So finally then, is wood fiber expensive? Yes, most natural fibers tend to be slightly more expensive than sort of the similar synthetic insulations. But my question would be, what is the comparison? Will the insulation perform in the real world as well as on paper with materials that shrink? That's doubtful. And also you need to compare materials when they are installed properly. So it's very easy to install materials badly. We generally try and encourage people to install them properly. There is a cost to that, but it means that you get a building that works. Do they have similar psi values for SAP? So because wood fiber tends to have very low heat loss through the junctions, that's what the psi values give you. You can actually target higher U values than you would with other materials and get the same SAP score. So it's really, those are important factors. I'll carry on and you can carry on.
Chris.
Thank you. Sorry about overrunning.
Rush you. No, we'll share the slides after.